The monster has awakened. Right now, as you listen to this, a dark wound on the surface of the Sun stretches wider than 130,000 kilometers across. That is 10 times the diameter of Earth, and it is pointing directly at us. What makes this terrifying is not its size alone. It is that we have seen something almost identical before. In 1859, a sunspot of nearly the same proportions unleashed what scientists now call the Carrington event, the most devastating solar storm in recorded human history. Telegraph lines caught fire. Operators were electrocuted at their stations. The night sky over the Caribbean glowed red with auroras that had no business being there. Now, 166 years later, we're staring at its twin. But here is what keeps scientists awake at night. In 1859, the world ran on steam and copper wire. Today, our civilization floats on satellites, pulses through fiber optic cables, and breathes through power grids that stretch across continents. A Carrington-class event striking Earth tomorrow would not just inconvenience us, it would erase the infrastructure of a modern life. The estimated damage exceeds $2 trillion. The blackouts could last not hours, not days, but years. And the sunspot that could trigger all of this is active right now, hurling plasma into space, building energy with every passing hour. By the time this documentary ends, you will understand exactly what we are facing, why the next few weeks matter more than any other moment in the last decade of solar observation, and what the scientific community is too afraid to say out loud. Before we begin, always remember to like this video. It tells your algorithm that you love these topics, and that you want more content just like this. And if you enjoy our calming deep dives into the mysteries of the cosmos, do not forget to subscribe and hit that notification bell so you never miss an update. Now tell me in the comments, where are you listening from right now? What time is it there? And have you ever witnessed a solar storm or aurora in your lifetime? I'm always curious to hear your stories. Now let us step into the fire. The sun does not sleep. We think of our star as this constant, reliable presence, rising each morning and setting each evening with mechanical predictability. But that image is a comforting illusion. The reality is far more violent. Beneath that golden disk lies a churning ocean of plasma, a sphere of hydrogen and helium undergoing constant nuclear fusion, at temperatures exceeding 15 million degrees Celsius in its core, and on its surface, where temperatures drop to a mere 5,500 degrees, something strange emerges from time to time. Dark patches, cooler regions where intense magnetic field lines have become so concentrated, so tangled, that they actually inhibit the convective flow of heat from below. We call these sunspots, and they are the birthplaces of chaos. On November 28th, 2025, something extraordinary rotated into view on the sun's eastern limb. Astronomers watching their monitors noticed a dark region emerging, but as hours passed, it became clear this was no ordinary sunspot. It kept coming and coming. It took more than 2 full days for the entire structure to rotate fully onto the Earth-facing side of the Sun. When it finally revealed itself in its entirety, the scientific community fell silent. The complex, now designated AR4294-4296, spans an area so vast that NOAA was forced to split it into 3 separate numbered regions simply because their classification systems could not handle its scale. 130,000 kilometers of magnetically tortured solar surface, multiple cores, each one the size of Earth, and at its heart, a magnetic configuration so complex that scientists have given it the most dangerous designation possible, Beta Gamma Delta. Think about that for a moment. We have classification systems specifically designed to tell us how likely a sunspot is to explode, and this one has earned the highest threat level we can assign. Beta Gamma Delta means the magnetic field lines within this region are not merely complex, they are chaotically intertwined, twisted around each other like snakes fighting in a bag. When magnetic field lines of opposite polarity get forced together with this kind of intensity, they do not simply coexist, they annihilate each other. And when that annihilation occurs, the energy stored in those twisted fields gets released in a fraction of a second. The result is a solar flare, a burst of electromagnetic radiation so powerful it can cross 93 million miles of space and ionize Earth's upper atmosphere in just 8 minutes. But here is where things get truly unsettling. On December 1st, the Sun did exactly what scientists feared it might. An X1.9 class solar flare erupted, not from AR4294 itself, but from a neighbouring region called AR4299 that had just rotated back into view. This was a region we had seen before, back in November, when it triggered stunning auroras visible across much of the Northern Hemisphere. Now it was back, and it announced its return with one of the most powerful flares we have seen this year. The explosion ionized the atmosphere over Australia and Southeast Asia, causing radio blackouts that affected aviation and maritime communications for approximately 30 minutes. Satellites detected the surge. Instruments on Earth confirmed the disruption. And all of this was just the opening act. The real concern is what comes next. You see, solar flares are only half the story. When those magnetic field lines snap and reconnect, they do more than emit radiation. They can also hurl physical matter into space, billions of tons of charged particles, protons and electrons, travelling at speeds that can exceed 7 million kilometers per hour. We call these eruptions coronal mass ejections, CMEs, and they are the true harbingers of geomagnetic chaos. A flare reaches Earth in 8 minutes because it travels at the speed of light. A CME, being made of actual matter, takes longer, usually between 1 and 3 days, depending on its velocity. And when that wall of charged particles slams into Earth's magnetic field, it creates something called a geomagnetic storm. On December 6th, the Sun struck again. AR4299 produced an M8.1 flare just shy of X-class, but this time the geometry was different. This time the explosion launched a full halo CME, meaning the ejection is heading straight for Earth. The velocity measurements are staggering, 1,143 kilometers per second. That is over 2.5 million miles per hour. NOAA has issued a G3 strong geomagnetic storm watch for December 9th. And as of this recording, that storm is either imminent or already beginning to interact with our planet's magnetosphere. Let that sink in. We are not discussing theoretical scenarios. We are not speculating about what might happen someday. This is happening right now. The CME is in transit, the sunspot complex remains active, and the magnetic configuration that could produce an even larger event is still intact, still pointed at Earth, still building energy. What fascinates and terrifies researchers in equal measure is the comparison being drawn between AR4294 and the sunspot that triggered the Carrington event. Richard Carrington was a British astronomer who, on September 1st, 1859, happened to be observing the Sun through his private telescope when he witnessed something no human had ever documented before. A brilliant white light flashed across the surface of a large sunspot group, intensified for approximately 5 minutes, and then faded. He had no idea what he was seeing. He rushed to find a witness, but by the time he returned, the phenomenon was already diminishing. What Carrington had observed was the first recorded solar flare in human history. 17 hours later, the sky caught fire. Auroras erupted across the planet, visible not just in the Arctic and Antarctic, but in Cuba, Hawaii, Colombia, even as far south as Santiago, Chile. In the Rocky Mountains of the American West, gold miners woke in the middle of the night, convinced it was dawn, and began preparing breakfast. In the northeastern United States, people reportedly read newspapers by the light of the aurora alone, but the beauty masked destruction. Telegraph systems, the most advanced technology of the era, went haywire. Operators reported receiving severe electric shocks. Machines sparked and smoked without any batteries connected. In several locations, telegraph paper caught fire spontaneously. The electromagnetic disturbance was so intense that it induced currents in every conductor it touched. Now look at the sunspot currently facing Earth. When spaceweather.com superimposed Carrington's original 1859 sketch over modern imagery of AR4294, the resemblance was immediate and alarming. The current complex covers approximately 90% of the area that Carrington's sunspot occupied. It displays the same multi-core structure, the same magnetic complexity, the same potential for catastrophic energy release. The main difference is that in 1859 the world depended on perhaps 100,000 miles of telegraph wire. Today we depend on 200,000 miles of high-voltage transmission lines, thousands of satellites, billions of internet-connected devices, and a global economy that would collapse within hours of losing electrical power. The question is no longer whether a Carrington-class event will happen again. The question is when. And looking at the solar surface right now, looking at the data streaming in from NASA's Solar Dynamics Observatory, from NOAA's GOES satellites, from amateur astronomers around the world photographing the sun through hydrogen alpha filters, the answer might be sooner than anyone wants to admit. But size alone does not determine whether a sunspot will erupt. The magnetic field configuration matters enormously. The rate at which new magnetic flux emerges from below the solar surface matters. The shear forces between regions of opposite polarity matter, and perhaps most importantly, chance matters. We have seen giant sunspots rotate across the face of the sun without producing a single significant flare. We have seen tiny, seemingly insignificant regions explode with X-class fury. The sun does not follow our predictions. It follows physics, and the physics of magnetic reconnection involves variables we cannot measure with perfect precision. What we can measure is probability. And right now, the probability assessments are sobering. NOAA's Space Weather Prediction Center has been issuing daily forecasts that place the chance of M-class flares at 70% and X-class flares at 15 to 20% for the period, while AR4294 remains on the Earth-facing disk. Those numbers might sound modest until you realize that we are talking about the potential for multiple major eruptions over a period of approximately 2 weeks. Each one is a roll of the dice. Each one could be the trigger for something far worse than what we experienced on December 1st or December 6th. And here is the detail that truly keeps solar physicists watching their instruments with nervous anticipation. The sunspot complex has been remarkably quiet considering its size. For 3 days straight, mathematical models showed a 30 to 70% probability of X-class flares, yet not a single M-class event occurred during that window. The region just sat there, absorbing energy, twisting its magnetic field lines tighter and tighter, like a coiled spring waiting to release. When a sunspot of this magnitude stays quiet for this long, it means one of two things. Either it is stabilizing and will rotate harmlessly off the western limb without incident, or it is storing energy for an explosion that will dwarf anything we have seen in years. There is no way to know which outcome awaits us, and that uncertainty is what makes the next several days so critical to monitor. 90% of a nightmare. When astronomers first began comparing the current sunspot complex to historical records, they reached for the most famous solar event in human memory. The Carrington event of 1859 has become the benchmark against which all extreme space weather is measured. It is the storm that proved the sun could reach out and touch our technology. It is the event that demonstrated in unmistakable terms that we are not isolated from our star. And now, 166 years later, we find ourselves staring at something hauntingly familiar. The measurements are striking. AR4294 through 4296, when analysed for total area coverage, spans approximately 2,300 millionths of the solar hemisphere. To put that in perspective, a millionth of the solar hemisphere is roughly equivalent to 3 million square kilometres, about the size of India. So we are talking about a dark region on the sun that, if transplanted to Earth, would cover most of a continent. This makes it one of the largest sunspot complexes observed in the 21st century, rivaled only by the infamous region 486 from October and November of 2003, which produced two of the most powerful solar flares ever recorded. But the comparison that has captured the imagination of both scientists and the public is the one to Richard Carrington's 1859 sunspot. When researchers at spaceweather.com overlaid Carrington's original hand-drawn sketch onto modern imagery of the current complex, the resemblance was immediate. The multi-lobed structure, the distribution of dark umbral cores surrounded by lighter penumbral regions, even the overall orientation on the solar disk, all of it echoed across more than a century and a half of time. The current complex covers approximately 90% of the area that Carrington documented. 90% of a nightmare. Think about what that means. We are not looking at a sunspot that is somewhat similar to the one that caused global technological disruption in 1859. We are looking at something that is, for all practical purposes, its near identical twin. The only significant difference in scale is that final 10%. a margin so slim that it provides almost no comfort whatsoever. The question that immediately arises is whether size alone determines the danger, and here this science becomes more nuanced than headlines might suggest. A large sunspot does not automatically produce large flares. The relationship between sunspot area and flare productivity is correlational, not deterministic. What matters far more than raw size is the magnetic complexity within the region, the rate at which new magnetic flux is emerging from beneath the solar surface, and the degree of shear between regions of opposite magnetic polarity. On all three of these metrics, AR4294 scores disturbingly high. The beta-gamma-delta classification it has received indicates the most complex possible magnetic configuration, one where positive and negative polarities are so thoroughly intermixed that the potential for violent reconnection events exists throughout the entire structure. New flux has been observed emerging continuously since the region first rotated into view, adding energy to an already stressed system. And the shear measurements, which track how much the magnetic field lines are being twisted and displaced from their equilibrium positions, are among the highest recorded for any sunspot this solar cycle. What we are witnessing is not merely a large sunspot. We are witnessing a magnetically loaded weapon pointed at Earth. The Carrington event itself offers a glimpse of what such a weapon can do when it fires. On September 1st, 1859, Carrington observed what he described as two patches of intensely bright and white light breaking out on the solar surface. The phenomenon lasted approximately 5 minutes before fading. He had no framework for understanding what he had seen. The concept of a solar flare did not yet exist. But he was methodical enough to record the exact time and position of the event, documentation that would prove invaluable in the decades to come. What Carrington witnessed was the release of energy that had been building in the twisted magnetic fields of that enormous sunspot. When field lines of opposite polarity are forced together, they can undergo a process called magnetic reconnection, where the field geometry fundamentally restructures itself into a lower energy state. The difference between the initial and final energy states is released instantaneously, producing electromagnetic radiation across the entire spectrum, from radio waves through visible light and ultraviolet, all the way to X-rays and gamma rays. The 1859 event is estimated to have been an X-45 class flare, a magnitude that almost defies comprehension. For reference, the most powerful flare recorded by modern instruments was approximately X-28 during the Halloween storms of 2003, and even that measurement is uncertain because it saturated the detectors. An X-45 flare would release roughly twice as much energy. It would ionize Earth's dayside atmosphere so thoroughly that high-frequency radio communication would be impossible for hours. The radiation pulse would arrive at Earth in 8 minutes, travelling at the speed of light, and there would be no practical way to prepare for its effects. But the flare itself, as dramatic as it was, caused only temporary disruption. The real damage came from what followed. The same magnetic reconnection event that produces a solar flare can also accelerate billions of tons of solar plasma to enormous velocities, launching it into interplanetary space as a coronal mass ejection. The Carrington event CME was exceptionally fast. It reached Earth in just 17.6 hours, a journey that typically takes 2 to 3 days. Researchers believe this remarkable speed was possible because a previous CME, launched a few days earlier, had cleared the ambient solar wind out of the way, creating a kind of vacuum tunnel through which the September 1st ejection could race unimpeded. When that wall of magnetized plasma struck Earth's magnetic field, it compressed the magnetosphere and triggered the most intense geomagnetic storm ever recorded. The DST index, which measures the strength of geomagnetic disturbances, plunged to an estimated negative 1,700 nanoteslas. Modern severe storms typically bottom out around negative 200 to negative 300. The Carrington event was roughly 5 to 6 times more intense than anything we have experienced in the space age. The auroral displays that resulted from this collision were unlike anything in living memory. Normally, auroras are confined to high latitudes, visible from places like Alaska, Scandinavia, and Antarctica. During the Carrington event, the auroral oval expanded so dramatically that the northern lights were seen in Cuba, Jamaica, and Hawaii. The southern lights reached Colombia and central Chile. In both hemispheres, The displays were described in terms that border on the apocalyptic. Blood-red curtains of light rippled across the sky. Pulsing green and violet bands stretched from horizon to horizon. The illumination was so bright that people could read newspapers outdoors at midnight. For those who did not understand what they were witnessing, the spectacle must have been terrifying. Religious interpretations were common. Some believed they were seeing the end times. Others thought the sky itself was on fire. But beneath the celestial beauty, a more practical crisis was unfolding. Telegraph systems around the world began to fail. Operators reported sparks shooting from their equipment. Some received painful electric shocks merely by touching the metal components of their stations. In several documented cases, telegraph paper caught fire and burned. The most remarkable reports, however, described something that seemed impossible. Operators who disconnected their batteries found that their equipment continued to work, powered entirely by the auroral currents surging through the wires. Messages were sent between Boston and Portland, Maine, using nothing but the electricity being induced by the geomagnetic storm. This was humanity's first direct encounter with the phenomenon we now call geomagnetically induced currents, or GICs. When Earth's magnetic field fluctuates rapidly, as it does during a geomagnetic storm, those fluctuations induce electric fields in the ground itself. Any long conductor, whether a telegraph wire, a power line, or a pipeline, will pick up these induced currents and allow them to flow. In 1859, the only long conductors in existence were telegraph wires, so the damage was limited to that technology. But the principle demonstrated in that event applies equally well to the infrastructure of the modern world. Today, we have approximately 200,000 miles of high-voltage transmission lines crisscrossing North America alone. We have natural gas pipelines stretching thousands of kilometers. We have undersea cables carrying internet traffic between continents. Every single one of these systems is vulnerable to the same phenomenon that set telegraph stations ablaze in 1859. The difference is one of scale. A Carrington-level event today would not merely disrupt communications for a few hours. It would threaten the foundations of technological civilization. The sunspot we're watching right now has 90% of the physical characteristics that produced that historic catastrophe. It has already demonstrated its capacity for violence, with the X1.9 flare on December 1st and the M8.1 flare on December 6th. The CME launched by that second event is currently in transit, expected to arrive within hours of this recording. And through it all, the primary complex AR4294 has remained eerily quiet, storing energy rather than releasing it. Amateur astronomer Patricio Leon, who's been tracking this region since it first appeared, noted something remarkable about its emergence. The sunspot complex required more than 2 full days to rotate entirely past the eastern limb of the Sun. 2 days. For context, the Sun rotates approximately 13 degrees per day as seen from Earth. A structure that takes 2 days to fully emerge must therefore span at least 26 degrees of solar longitude, an enormous arc that testifies to the sheer physical scale of what we're dealing with. Leon also noted the delta magnetic component, the most dangerous classification, and observed that now that the region is fully Earth-facing, we are exposed to whatever activity it may produce. There is no longer any buffer. The barrel of the gun, if you will pardon the metaphor, is pointed directly at us. NOAA has divided the complex into 3 separate numbered regions: AR4294, AR4296, and AR4298, because their cataloguing systems were not designed to handle a single structure of this magnitude. This administrative decision underscores just how exceptional the current situation is. We are not dealing with routine solar activity. We are dealing with something that pushes against the limits of our classification frameworks. The comparison to the Carrington event is not mere sensationalism. It is a sober recognition that the Sun is capable of producing storms that would fundamentally alter human society, and that the current solar configuration bears an uncomfortable resemblance to the conditions that preceded the most extreme such storm on record. 90% of a nightmare is still close enough to keep scientists watching their screens with growing unease. And here is the detail that transforms unease into genuine concern. The Carrington event occurred during solar cycle 10, near the solar maximum of 1860. We are currently in solar cycle 25, and although NOAA's official position is that the cycle peaked sometime in 2024, The sun has not received that memo. Activity remains elevated. Sunspot counts exceeded predictions throughout most of this cycle, and the emergence of AR4294 during what should be the declining phase of solar maximum suggests that we may not have seen the last of the fireworks. The next few days will reveal whether this sunspot complex follows the path of its 1859 predecessor or fades quietly as it rotates toward the western limb. Either outcome is possible, but the mere existence of this region, its scale, its magnetic complexity, and its obvious family resemblance to history's most destructive solar storm demands that we pay attention. 90% of a nightmare is close enough to count. The day the sun set, telegraph wires on fire. The morning of September 1st, 1859 began like any other for Richard Christopher Carrington. The 33-year-old English astronomer had established a private observatory near Redhill in Surrey, where he dedicated himself to the systematic study of sunspots. He was meticulous, methodical, and possessed of the patience required to spend hours each day projecting the solar image through his telescope and carefully sketching what he observed. He had no idea that this particular morning would immortalize his name in the annals of science. At approximately 11:18 in the morning local time, Carrington was engaged in his usual routine, documenting a large group of sunspots that had been visible for several days. The group was impressive, covering an area easily visible through properly filtered optics, but there was nothing about it that suggested impending violence. Then, without warning, two patches of intensely bright and white light erupted from the dark cores of the sunspot group. Carrington later described the phenomenon as appearing like two beads of brilliant white, far exceeding the luminosity of the surrounding solar surface. He was stunned. In all his years of solar observation, he had never witnessed anything like it. His first instinct was scientific. He needed a witness to confirm what he was seeing. He rushed from his observing chair to find someone, anyone, who could corroborate this extraordinary event. By the time he returned, less than 60 seconds later, the phenomenon was already fading. The two bright points had expanded slightly and diminished considerably in intensity. Within 5 minutes, they had vanished entirely, leaving behind the same sunspot group that had been there before, apparently unchanged. But Carrington knew he had seen something unprecedented. He recorded the precise time, the exact position on the solar disk, and every detail he could recall about the appearance and evolution of the light. What Carrington did not know, could not have known, was that he had just witnessed the first documented solar flare in human history. The concept did not exist. The mechanism was unknown. The connection between solar events and terrestrial effects was purely speculative. But in that moment, watching those 2 points of white fire fade into the ordinary brightness of the sun, Carrington became the first human being to directly observe the phenomenon that would, one day, threaten to bring down civilization. He was not the only observer that morning. Richard Hodgson, another English astronomer, was independently monitoring the sun from a different location and witnessed the same event. The two men would later publish their observations side by side in the monthly notices of the Royal Astronomical Society, providing crucial corroboration that the event was real and not an artifact of instrumentation or imagination. 17 hours and 40 minutes after Carrington watched the white light fade, the consequences of what he had seen arrived at Earth. The first indication that something unusual was happening came from compass needles. Magnetometers, instruments designed to measure the strength and direction of Earth's magnetic field, began behaving erratically. At the Kew Observatory outside London, Scottish physicist Balfour Stewart was monitoring a recording magnetometer when the needles suddenly pinned against their stops. The fluctuations were so extreme that the instruments could not track them. Something was disturbing Earth's magnetic field on a scale never before recorded. Then the sky began to glow. Auroras are nothing new to observers at high latitudes. The dance of coloured light across polar skies has been documented for millennia, woven into mythology and folklore from Scandinavia to northern Canada. But what appeared on the night of September 1st and continued through September 2nd was not a typical auroral display. It was a global phenomenon, visible from locations where auroras had never been seen before and might never be seen again in a human lifetime. In the American West, gold miners working in the Rocky Mountains were jolted awake by the strange illumination. Convinced that dawn had arrived early, they rose from their bedrolls and began preparing breakfast, only to discover that it was still the middle of the night. The sky blazed with crimson and green light, bright enough to cast shadows, bright enough to read by. Similar reports emerged from across the northern and southern hemispheres. In Queensland, Australia, observers noted brilliant red glows on the horizon. In Chile, astronomers documented auroras extending far north of their normal range. In the Caribbean, populations who had never seen such phenomena stared skyward in wonder and terror. The New York Times dispatched reporters to cover the strange event, and their accounts paint a vivid picture of public reaction. In cities across the northeastern United States, people gathered in streets and parks to watch the celestial display. Some believed they were witnessing a sign from God. Others feared it heralded the end of the world. A few, more scientifically inclined, suspected that something unusual was happening on the sun. But while millions of eyes gazed upward in amazement, a quieter crisis was unfolding in telegraph offices around the planet. The telegraph system of 1859 represented the cutting edge of human technology. First demonstrated commercially in the 1840s, it had expanded with remarkable speed. By the time of the Carrington event, approximately 100,000 miles of telegraph wire crisscrossed Europe and North America, connecting cities, coordinating commerce, and transmitting news at speeds that had seemed impossible just a generation earlier. Journalists called it the Victorian Internet, and the comparison was apt. For the first time in human history, information could travel faster than a horse or a ship. On the night of September 1st, this revolutionary network began to fail. The problem started subtly. Operators noticed that their equipment was behaving strangely, producing erratic signals and requiring unusual adjustments to maintain communication. As the auroral display intensified, so did the interference. Sparks began jumping from telegraph keys and sounder mechanisms. Operators reported painful electric shocks when they touched metal components. In several offices, the sparks were intense enough to ignite the paper tape used to record incoming messages. Small fires broke out at telegraph stations from Boston to Brussels. The American Telegraph Company office in Boston provides one of the best documented accounts of what happened. Operators arrived for their morning shift on September 2nd to find that sending and receiving messages was nearly impossible. The instruments fluctuated wildly, signals were garbled beyond recognition, and the equipment seemed to have developed a mind of its own. After several hours of frustration, an operator made a discovery that seemed to violate everything known about electrical engineering. He disconnected the batteries. In normal operation, telegraph systems required batteries to generate the electrical current that carried signals through the wires. Without batteries, there should have been no current, no signal, no communication. But when the Boston operator removed his batteries from the circuit, the equipment continued to function. Messages were successfully exchanged between Boston and Portland, Maine, using nothing but the current being induced in the wires by the geomagnetic storm itself. The aurora was powering the telegraph. This phenomenon, while appearing almost magical to 19th century operators, has a straightforward physical explanation. When Earth's magnetic field fluctuates rapidly, as it does during a severe geomagnetic storm, those fluctuations induce electric fields in the crust of the planet. Any conductive material in contact with the ground, such as the grounded telegraph wires of the era, will pick up these induced electric fields and allow current to flow. The longer the conductor, the greater the voltage that accumulates along its length. Telegraph lines, stretching hundreds of miles between stations, acted as enormous antennas, collecting the auroral electricity and funneling it into equipment designed to operate on tiny battery voltages. The same effect that allowed operators to send messages without batteries also produced the sparks, shocks, and fires that plagued the system. The induced currents were not stable or controlled. They fluctuated with the varying intensity of the geomagnetic storm, surging and ebbing unpredictably. Equipment designed for milliamp currents found itself conducting tens or even hundreds of times that amount. Insulation failed, contacts overheated, paper ignited. Reports from telegraph offices around the world tell similar stories. In Philadelphia, operators observed sparks showering from their instruments and described fantastical and unreadable messages appearing on their equipment. In Washington, an operator named Frederick Royce received a severe electric shock. that stunned him for an instant, as reported in contemporary newspaper accounts. In Victoria, Australia, the General Superintendent of Electric Telegraph, Samuel McGowan, compiled a formal report for the Victorian Parliament documenting the interruptions to telegraphic communication throughout the colony. The disruption lasted approximately 2 days, coinciding with the duration of the most intense geomagnetic disturbance. As the storm subsided and Earth's magnetic field returned to normal, telegraph operations gradually resumed. Damaged equipment was repaired or replaced. The fires had been small enough to extinguish, without major property loss. By the end of the first week of September, the Victorian internet was back online, and for most people, the strange events were already fading into memory. But for a handful of scientists, the Carrington event raised profound questions. Richard Carrington himself noted the coincidence between the solar flare he had observed and the geomagnetic storm that followed, but he was cautious about claiming a direct causal connection. "One swallow does not make a summer," he wrote, acknowledging that correlation does not prove causation, yet the timing was suggestive. A brilliant eruption on the Sun followed less than 18 hours later by the most intense geomagnetic disturbance in recorded history. Could the Sun truly reach out and touch the Earth in this way? It would take decades of additional research to confirm what Carrington suspected. The connection between solar flares, coronal mass ejections, and geomagnetic storms is now well established. We understand the physics. We can predict, with reasonable accuracy, when a solar storm will arrive and how intense it might be. What we cannot do, despite all our technological advancement, is prevent the consequences. The telegraph wires of 1859 have been replaced by power grids and fibre optic cables. The batteries that powered those early instruments have given way to transformers and capacitors operating at voltages that would have seemed inconceivable to Victorian engineers. But the fundamental vulnerability remains unchanged. Long conductors pick up geomagnetically induced currents. The longer the conductor and the more intense the storm, the greater the voltage and the more severe the potential damage. The Carrington event set telegraph paper on fire. A similar event today would do far worse, and as mentioned before, the sunspot currently facing Earth bears an uncomfortable resemblance to the one that Richard Carrington was sketching on that September morning when 2 points of white fire changed the way we think about our relationship with the Sun. 92 seconds to darkness. The lessons of the Carrington event faded quickly from public memory. By the early 20th century, most people had forgotten that the Sun could reach out and disrupt human technology. The telegraph had been superseded by the telephone, then by radio, and eventually by the complex electrical infrastructure that defines modern life. Power grids expanded across continents. High-voltage transmission lines carried electricity from remote generating stations to hungry cities, and all of it was built without serious consideration of what a severe geomagnetic storm might do. The warning came on March 13th, 1989. It came to a province in Canada that had done nothing wrong, whose citizens were simply going about their lives on an ordinary Monday night in late winter, and it came with a speed and ferocity that stunned even the experts who should have seen it coming. The solar storm that struck Earth on that date originated from a sunspot region, designated 5395. It was an impressive active region, sprawling across the solar disk and crackling with magnetic energy. Between March 6th and March 13th, it produced more than a dozen M-class and X-class solar flares, including an X4.5 event on March 10th and an M7.3 on March 12th. Each of these eruptions launched coronal mass ejections into space, creating a kind of celestial traffic jam of plasma clouds racing toward Earth. The first CME arrived and passed without major incident. It disturbed Earth's magnetic field, produced some modest auroral activity at high latitudes, but caused no significant damage to infrastructure. What it did do, however, was sweep aside the ambient solar wind ahead of it, clearing a path through interplanetary space. When the second CME arrived, travelling faster because it encountered less resistance, the impact was dramatically amplified. At 1:27 in the morning Universal Time on March 13th, which corresponds to late evening on March 12th in eastern North America, the main event began. The geomagnetic storm that erupted in the following hours would be classified as a G5, the highest level on NOAA's space weather scale. Auroras blazed across the sky, visible not just in Canada and Alaska, but as far south as Texas, Florida, and Cuba. The displays were so vivid, so unexpected in subtropical latitudes, that some observers feared they were witnessing the opening salvos of nuclear war. The Cold War was in its final years, tensions remained high, and a blood-red sky over Miami seemed more consistent with atomic holocaust than solar physics. While millions of people stared upward in wonder or alarm, the real crisis was building underground and along the high-voltage transmission lines of the Hydro-Quebec power system. Quebec presents a unique vulnerability to geomagnetic storms. The province sits atop the Canadian Shield, a vast formation of ancient igneous rock that extends beneath much of eastern Canada. This rock, formed billions of years ago, is electrically resistive. When geomagnetically induced currents try to flow through the Earth, as they do during a magnetic storm, the Canadian Shield blocks them. The currents must find another path, and in a province crisscrossed by long transmission lines, the path of least resistance leads directly into the power grid. Hydro-Quebec's system was designed to transmit electricity over enormous distances. The province generates much of its power from hydroelectric dams in the remote James Bay region, hundreds of kilometres north of Montreal and Quebec City. Getting that power to consumers requires transmission lines that stretch across vast stretches of wilderness, lines that act as perfect antennas for collecting geomagnetically induced currents. At 2:44 in the morning on March 13th, the storm currents found their way into the system. Within seconds, unusual frequencies called harmonics began flowing through the grid. These harmonics caused static compensators, devices used to regulate voltage on long transmission lines, to trip offline at the Chibougamau and La Vérendrye substations. The loss of these compensators destabilized the grid, causing voltage oscillations and power swings that cascaded through the network. In 92 seconds, it was over. The entire Hydro-Quebec grid collapsed. 21,000 megawatts of generating capacity went dark. 6 million people found themselves without electricity in the middle of a cold March night. Traffic lights went dead. Elevators stopped between floors. Hospitals switched to backup generators. The Montreal Metro ceased operation during the morning rush hour that followed. Dorval Airport closed. Schools and businesses could not open because there was no power to heat the buildings or light the classrooms. For 9 hours, the province of Quebec remained in darkness. Engineers worked frantically to restore service, but the process was slow and complicated. Some of the key equipment on the James Bay transmission network had been damaged by the event, requiring repairs before power could be safely restored. When the lights finally came back on, the scale of what had happened began to sink in. David Boatler, who would later become head of the Space Weather Group at Natural Resources Canada, called the 1989 event the biggest geomagnetic storm of the space age. It became the archetypal disturbance for understanding how solar activity can cause blackouts. For the first time, a modern industrial society had experienced firsthand what the Carrington event only hinted at. The sun could take down a power grid, and it could do so in less than 2 minutes. The economic impact was substantial but manageable. Quebec's blackout lasted hours, not days or weeks. Most residential and commercial customers experienced inconvenience rather than catastrophe. But the event exposed vulnerabilities that had the potential for far greater damage under more extreme conditions. The New York power pool lost 150 megawatts of generating capacity at the moment Quebec collapsed, a consequence of interconnections between the two systems. Across the United States, more than 200 grid anomalies were recorded within minutes of the storm's onset. A transformer at the Salem nuclear power plant in New Jersey overheated and failed. Operators across North America found themselves scrambling to respond to a threat that most of them had never seriously trained for. In orbit, satellites experienced their own problems. NASA's TDRS-1 communication satellite recorded over 250 anomalies as energetic particles from the storm flooded its sensitive electronics. GOES weather satellites lost communications temporarily, disrupting the imagery used for weather forecasting. The Space Shuttle Discovery, which had launched just hours earlier, experienced a mysterious fuel cell sensor malfunction that persisted until the storm subsided. The March 1989 storm was not a Carrington-level event. Estimates suggest it was roughly one-third as intense as the 1859 superstorm, yet it was sufficient to black out an entire province for 9 hours, damage transformers, disrupt satellites, and demonstrate conclusively that modern infrastructure was vulnerable to space weather in ways that few had previously appreciated. Hydro-Quebec learned from the experience. In the years following the blackout, the utility invested approximately $2 billion in upgrades designed to prevent a recurrence. They recalibrated protective relays to be less sensitive to harmonic disturbances. They installed series compensation on transmission lines to enhance grid stability. They established real-time monitoring systems to track geomagnetic disturbances as they develop. According to utility engineers, the modern Hydro-Quebec grid can withstand a 1-in-100-year geomagnetic event. The March 1989 storm was approximately a 1-in-50-year event. But what about a 1-in-500-year event? What about the Carrington event? The uncomfortable truth is that we do not know whether modern power grids could survive a storm of that magnitude. The transformers that form the backbone of high-voltage transmission systems are particularly vulnerable. These massive devices, which step voltage up for efficient long-distance transmission and step it down again for distribution to consumers, can be damaged by sustained exposure to geomagnetically induced currents. The currents cause the transformer cores to saturate, leading to overheating that can destroy the insulation and render the transformer inoperable. The problem is compounded by the nature of these devices. Extra high-voltage transformers are not mass-produced commodities that can be quickly replaced. They are custom-engineered for specific applications, manufactured by a handful of companies worldwide, and require months or even years to procure. If a severe geomagnetic storm damaged dozens or hundreds of these transformers simultaneously, the replacement parts would simply not exist. Grid operators would face the prospect of extended blackouts while they waited for new equipment to be built and shipped from overseas factories. The National Academies of Sciences commissioned a study in 2008 that examined the potential impact of a Carrington-level event on modern infrastructure. The conclusions were sobering. The US population at risk of extended power outage was estimated at 20 to 40 million people. The duration of those outages could range from 16 days to 1 to 2 years, depending on the extent of transformer damage and the ability to manufacture replacements. The economic cost was projected to approach $2 trillion. These are not the projections of alarmists. They are the consensus estimates of engineers, physicists, and economists who have studied the problem carefully. A Carrington-level event would not merely inconvenience us. It would threaten the functioning of civilization in affected regions for months or years. The sunspot currently facing Earth has demonstrated its capacity for X-class flares. The CME currently in transit will test our defences over the next few days. And through it all, the memory of March 13th, 1989, serves as a reminder that the sun does not respect our schedules, our infrastructure investments, or our assumptions about the reliability of the systems we depend on. 92 seconds. That was all it took to plunge 6 million people into darkness. The question that haunts space weather researchers is not whether it will happen again. The question is whether next time it will be worse. Trees, remember what we have forgotten. There is a witness to events that occurred long before any human being kept records. A silent chronicler that has been documenting cosmic catastrophes for thousands of years, preserving evidence in its very cells, waiting for someone to learn how to read its testimony. That witness is the tree. In 2012, a doctoral student at Nagoya University in Japan made a discovery that would reshape our understanding of the sun's destructive potential. Fusa Miyake was studying the rings of a 1900-year-old Japanese cedar, measuring the concentration of radioactive carbon-14 in each annual growth layer. Carbon-14 is produced when cosmic radiation strikes nitrogen atoms in Earth's atmosphere, and it gets incorporated into living things through the carbon cycle. Normally, the concentration is relatively stable from year to year, varying only slightly with the 11-year solar cycle. But in one ring, corresponding to the years 774 and 775 of the Common Era, Miyake found something extraordinary. The carbon-14 concentration had spiked by 12%, roughly 20 times greater than the ordinary fluctuations caused by cosmic rays. Something had bathed Earth in an enormous pulse of radiation over 1,000 years ago, something far more powerful than anything recorded in human history. Miyake's discovery was independently confirmed by research teams around the world. The same spike appeared in tree ring samples from Germany, Russia, the United States, Finland, and New Zealand. Whatever had caused this event, it was global in scope. Trees on every continent had recorded it, preserving the evidence in their growth rings like a message in a bottle waiting to be discovered. The scientific community scrambled to explain what could have produced such an intense burst of radiation. Several hypotheses were proposed. Perhaps a nearby supernova had exploded, showering Earth with gamma rays. Perhaps a cosmic gamma ray burst, the most energetic phenomenon in the universe, had briefly pointed at our planet. Perhaps a comet had struck the upper atmosphere, somehow generating the isotopic signature. But as more evidence accumulated, one explanation emerged as the most likely. The 774 event was probably a solar storm, but a solar storm of almost unimaginable intensity. Researchers began calling these events Miyake events, in honor of the scientist who first identified them. The Carrington event of 1859 has long been considered the worst case scenario for solar storms. We measure modern events against it, planning our defences around the assumption that something of similar magnitude represents the upper limit of what the sun can produce. But the Miyake event of 774 was at least 10 times more powerful. Some estimates place it at 20 times the intensity of the Carrington event. If that figure is accurate, then our historical benchmark for extreme space weather is not the worst case at all. It is merely a severe case, dwarfed by events that have occurred multiple times in the past 10,000 years. Since Miyake's initial discovery, researchers have identified at least 6 confirmed Miyake events in the tree ring record. They occurred in 7176 BCE, 5410 BCE, 5259 BCE, 660 BCE, 774 CE, and 993 CE. There may be others waiting to be discovered as scientists analyze more samples from more locations. Each one represents a moment when Earth was bombarded by radiation, far exceeding anything we have experienced in modern times. The existence of these events raises troubling questions. If the sun is capable of producing storms 10 or 20 times more powerful than the Carrington event, what would such a storm do to our civilization? We have estimated that a Carrington-level event could cause $2 trillion in damage and leave tens of millions of people without power for months. Scale that up by a factor of 10, and the numbers become almost incomprehensible. The radiation alone would pose significant risks. Modern satellites are hardened against the particle environment of space, but they are not designed to survive a Miyake-level bombardment. Every satellite in orbit, from GPS constellations to weather monitoring platforms to the communication networks that link our world together, could potentially be damaged or destroyed. Astronauts aboard the International Space Station would need to shelter in the most heavily shielded areas of the facility and might still receive radiation doses exceeding safe limits. Passengers on high-altitude aircraft would be exposed to increased radiation, particularly on polar routes. On the ground, the geomagnetically induced currents would be proportionally more intense. Power grids that might survive a Carrington event could face complete devastation from a Miyake-scale storm. The cascade of transformer failures, the extended blackouts, the slow collapse of supply chains as fuel and food distribution systems ground to a halt. All of it would be magnified to a degree that challenges our ability to model the consequences. Think about that for a moment. 6 times in the past 10,000 years, the sun has produced storms powerful enough to leave signatures in trees around the world. That averages to roughly once every 15 to 1700 years. We are currently living in a gap between events, a gap that has lasted more than 1,000 years since the 993 event. Statistically, we are due. Now, it's important to note that not all scientists agree that Miyake events are caused by solar storms. A study published in 2022 by researchers at the University of Queensland cast doubt on the solar flare hypothesis. Using statistical modelling of carbon cycle dynamics, they found no consistent correlation between Miyake events and the 11-year solar cycle. If solar flares were responsible, one would expect the events to cluster near solar maximum when flare activity is highest. But the tree ring data shows events occurring at various phases of the cycle, including during solar minimum. The Queensland team also found no clear latitudinal pattern in the intensity of the carbon-14 spikes. If solar energetic particles were responsible, One would expect trees closer to the poles to show larger spikes, since Earth's magnetic field funnels charged particles toward high latitudes. The data do not clearly show this expected pattern. These findings do not rule out solar storms as the cause of Miyake events, but they do suggest that our understanding is incomplete. Perhaps the events are not produced by single enormous flares, but by prolonged periods of intense activity, a storm of smaller flares rather than one catastrophic explosion. Perhaps the relationship between solar particle events and isotope production is more complex than our models assume. Perhaps some Miyake events have solar origins, while others result from different phenomena entirely. What the tree ring record tells us with certainty is that Earth has experienced radiation events far exceeding anything in recorded history. Whatever caused them, whether solar storms, gamma-ray bursts, or some other phenomenon, the events happened. They are not hypothetical scenarios or worst-case speculations. They are physical facts, recorded in wood and ice, waiting for us to take them seriously. The European Space Agency has begun incorporating Miyake-scale events into their planning for satellite protection. In tabletop exercises conducted recently, ESA engineers simulated the arrival of a Carrington-class CME and evaluated how they would protect the Sentinel-1D satellite from damage. The conclusion was sobering. If a storm of true Carrington magnitude struck Earth, the damage to satellite constellations could be extensive. For a Miyake-scale event, one participant noted, the immense flow of energy ejected by the Sun may cause damage to all our satellites in orbit. Not some satellites, all satellites. We have become utterly dependent on space-based infrastructure in ways that would have seemed like science fiction just a few decades ago. GPS navigation guides not just drivers and pilots, but also precision agriculture, construction surveying, and the timing synchronization that allows financial markets to function. Weather satellites provide the data that makes modern forecasting possible. Communication satellites connect remote communities, relay television broadcasts, and enable the global telecommunications network. Scientific satellites monitor everything from ocean temperatures to deforestation to the health of the ozone layer. Lose all of that in a single event, and the consequences ripple through every aspect of modern life. Recovery would take years, perhaps decades, as we struggle to rebuild constellations of satellites from a standing start. And all of this assumes that ground-based infrastructure survives well enough to support the recovery effort. The trees remember what we have forgotten. They remember that the Sun is capable of violence beyond our experience, that the Carrington event was not the ceiling, but merely a data point on a spectrum that extends far higher. As we watch the current sunspot complex evolve and track the CME heading toward Earth, it is worth keeping this perspective in mind. We are not preparing for the worst the Sun can do. We are preparing for events that fall comfortably within the normal range of solar variability. The truly extreme events, the ones that left their marks in ancient wood, represent a level of hazard that our civilization has never confronted and is not remotely prepared to survive. $1 trillion blind spot. There is a peculiar form of denial that afflicts modern technological societies. We build systems of extraordinary complexity, systems upon which tens of millions of lives depend, and then we systematically avoid thinking about the ways those systems might fail. The power grid is perhaps the most striking example. We flip switches and expect lights to illuminate. We plug in devices and expect them to charge. We assume, without conscious thought, that the invisible flow of electrons will continue indefinitely. The notion that the Sun could interrupt this flow, could potentially interrupt it for months or years, exists in a cognitive blind spot that we collectively choose not to examine. The numbers are staggering when you finally look at them directly. The North American power grid consists of approximately 200,000 miles of high-voltage transmission lines, thousands of generating plants, millions of transformers, and a web of digital control systems that coordinate the whole enterprise in real time. It is one of the largest and most complex machines ever constructed by human beings. And it was built without serious consideration of geomagnetic storm hazards. The fundamental vulnerability lies in those transformers, particularly the extra high voltage units that step power up for long-distance transmission and step it down again for distribution. These devices are engineering marvels, precisely wound coils of copper and iron that can handle enormous amounts of electrical energy. But they have a weakness. When geomagnetically induced currents enter a transformer, they cause the iron core to saturate magnetically. A saturated core cannot properly regulate voltage, leading to heating, harmonic distortion, and in extreme cases permanent damage to the windings and insulation. A damaged EHV transformer is not something you can fix with a trip to the hardware store. These units weigh hundreds of tons, cost millions of dollars, and require months or years to manufacture. There is no strategic reserve of spares sitting in warehouses waiting to be deployed. If a severe geomagnetic storm damaged dozens or hundreds of these transformers simultaneously across a continental grid, there would be no quick path to recovery. The factories that build them are located primarily overseas, in countries like South Korea and Germany. Even under emergency conditions, ramping up production to replace catastrophic losses would take years. The Lloyds of London study from 2013 attempted to put a price tag on this vulnerability. Their analysis focused on the potential impact of a Carrington-level event on the United States power grid. The conclusions were sobering. Depending on the severity of the storm and the extent of transformer damage, economic losses could range from $600 billion to $2.6 trillion. The upper estimate equals roughly 15% of annual US gross domestic product. It would be the most expensive natural disaster in human history by a wide margin. But the financial figures, as shocking as they are, only begin to capture the human cost. Modern life depends on electricity in ways that were inconceivable even a few decades ago. Consider what happens when the power goes out for an extended period. Heating and cooling systems stop functioning. In winter, pipes freeze and burst. In summer, vulnerable populations die from heat exposure. Food spoils in refrigerators and freezers. Water treatment plants cease operation, making tap water unsafe to drink. Sewage systems back up as pumping stations fail. Gas stations cannot pump fuel because their equipment requires electricity. Without fuel, emergency vehicles cannot respond to calls. Hospitals exhaust their backup generator capacity and begin transferring patients to unaffected regions, assuming unaffected regions exist. The supply chains that deliver food to grocery stores, medicine to pharmacies, and fuel to gas stations are precision-engineered for efficiency, not resilience. They operate on just-in-time principles with minimal buffer stocks. Within days of a widespread power outage, shelves begin to empty. Within weeks, urban populations face genuine scarcity. The social order that depends on the continuous flow of goods begins to fray. This is not speculation. We have seen glimpses of this future in localized events. Hurricane Maria struck Puerto Rico in 2017 and left much of the island without power for months. The official death toll was revised upward to nearly 3,000 as the delayed effects of infrastructure collapse accumulated. And that was an island of 3 million people with the full support of the mainland United States available for recovery operations. Now imagine the same scenario unfolding simultaneously across the eastern seaboard, the Midwest and parts of Canada. Imagine no unaffected region to send aid because everywhere is affected. Imagine the federal government trying to coordinate recovery operations while its own communications and logistics systems are compromised by the same storm that damaged the grid. The National Academy's study estimated that a Carrington-level event could leave 20 to 40 million Americans without power for extended periods. Extended periods in this context means anywhere from 16 days to 1 to 2 years. The variation depends entirely on how many transformers are destroyed and how quickly they can be replaced. Think about 16 days without power. Think about your community, your neighbors, your family, going more than 2 weeks without electricity in the middle of winter or the height of summer. Now think about a year. Think about what society looks like after 12 months of cascading infrastructure failure. And yet, despite these risks, we have done remarkably little to protect ourselves. The Federal Energy Regulatory Commission ordered the North American Electric Reliability Corporation to develop standards for grid protection against geomagnetic storms in 2013. Those standards have been slowly implemented, but they focus primarily on operational procedures rather than physical hardening. Utilities can reduce power flows during storm warnings, can configure their systems to minimize harmonic disturbances, can monitor GIC levels in real time. What they cannot easily do is retrofit the fundamental vulnerability out of equipment that was designed without geomagnetic storms in mind. There are technical solutions available. Blocking devices can be installed at transformer-neutral grounds to prevent GIC from entering the system. These devices are not prohibitively expensive, perhaps $40,000 to $50,000 per installation. Given the stakes involved, protecting the entire high-risk transformer fleet would cost perhaps $1 to $2 billion. For comparison, we spend more than that every year maintaining federal highways. We spend more than that on a single aircraft carrier. Yet the investment has not been made. Utilities operate under regulatory frameworks that reward cost minimization and punish capital expenditure. Spending billions to protect against an event that might not happen during any given executive's tenure is a hard sell to shareholders and regulators alike. The result is a $1 trillion blind spot, a known vulnerability that we collectively pretend does not exist, because confronting it would require action that no one wants to take. The Internet presents its own set of vulnerabilities. The backbone of global Internet connectivity consists of undersea cables stretching across ocean floors, connecting continents with fiber optic, threads that carry 99% of intercontinental data traffic. These cables are not especially vulnerable to direct geomagnetic effects, fiber optics being non-conductive, but the electronic repeaters that amplify signals along their length are another matter. A severe GIC event could potentially damage repeater equipment, disrupting intercontinental communications until repairs could be made. More concerning are the terrestrial data centers that store and process the information that modern life depends on. These facilities require enormous amounts of electricity, both to run the servers and to cool them. A prolonged power outage would force data centers offline, taking with them email systems, cloud storage, financial databases, and the countless other digital services we take for granted. Even with backup generators, most facilities can only maintain operations for a limited time before fuel runs out. GPS navigation, which now underpins everything from driving directions to precision agriculture to financial transaction timing, depends entirely on a constellation of satellites that would be directly exposed to a severe solar storm. The satellites themselves might survive, being hardened against normal space weather, but a Carrington or Miyake-level event could potentially damage their electronics or degrade their performance. Even temporary loss of GPS would cascade through countless systems that have come to depend on satellite navigation and timing. The common thread running through all these vulnerabilities is our failure to design for resilience. We have built systems that work extraordinarily well under normal conditions and catastrophically badly under extreme conditions. We have optimized for efficiency and cost minimization while treating resilience as someone else's problem. We have created a civilization that depends absolutely on technologies that can be switched off by the sun in the span of a few hours. The sunspot currently facing Earth may or may not produce a catastrophic storm. The CME currently in transit will probably cause auroras and minor disruptions rather than grid collapse, but sooner or later, our luck will run out. The Carrington event happened. The Quebec blackout happened. Miyake events happened. The sun does not care about our schedules, our infrastructure investments, or our preference for ignoring uncomfortable risks. At some point, and we cannot know when, we will have to confront this blind spot. The only question is whether we do so on our own terms, through careful preparation and strategic investment, or on the sun's terms, through disaster and recovery. The choice remains ours for now. The cycle. We cannot escape. The sun breathes. Not in the literal sense of drawing air into lungs, of course, but in a rhythmic pulsation of activity that has been documented for nearly 3 centuries. Every 11 years, give or take, our star transitions from a period of relative calm to a period of violent upheaval and back again. Sunspots multiply across its surface. Flares erupt with increasing frequency. Coronal mass ejections blast outward into the solar system. Then, gradually, the activity subsides, sunspots fade, and the sun enters another quiet phase before the cycle begins anew. We call this pattern the solar cycle, and we have been tracking it since 1755, when astronomers began systematically counting sunspots. The current cycle, Solar Cycle 25, began in December of 2019, when the smoothed monthly sunspot number dropped to its minimum value of just 1.8. Since then, activity has been climbing, and by most measures, we are currently at or near solar maximum, the peak of the cycle when the sun is at its most active and most dangerous. The predictions for cycle 25 were initially conservative. A panel of experts convened by NOAA, NASA, and the International Space Environment Services predicted in 2019 that the cycle would be similar in strength to cycle 24, which had been the weakest in a century. They forecast a maximum sunspot number of 115 occurring around July of 2025. The general expectation was for a relatively subdued maximum, with solar activity remaining below historical averages. The sun did not cooperate with this forecast. By early 2023, it became clear that solar cycle 25 was running ahead of schedule and exceeding predictions. Sunspot counts were higher than expected. Flare activity was more frequent. The revised forecast, issued by NOAA in October of 2023, called for a peak between January and October of 2024, with a maximum sunspot number between 137 and 173. Even this revised estimate proved conservative. In August of 2024, the smoothed monthly sunspot number reached 216, nearly double the initial prediction. We are now in December of 2025, and according to some interpretations of the data, we have passed the peak of the cycle. NOAA's latest update shows the November sunspot number at 91.8, down significantly from the August high. This suggests that solar cycle 25 is indeed declining, that we are past the most dangerous phase and heading toward the relative safety of solar minimum. But this interpretation comes with significant caveats. Solar cycles do not follow neat, predictable curves. They are messy, variable, punctuated by bursts of activity that can occur at any phase. Some of the most powerful events on record have occurred during the declining phase of a cycle, when the overall activity level was dropping but individual active regions still had the capacity for extreme behaviour. The Carrington event itself occurred in September of 1859, just a few months before the solar maximum of cycle 10. But the Quebec blackout of 1989 occurred in March, well into the declining phase of cycle 22. The timing of a major event within a cycle is less important than the characteristics of specific active regions. A single, magnetically complex sunspot can produce catastrophic flares regardless of where we are in the overall cycle progression. This brings us back to AR4294. The emergence of such a massive, magnetically complex sunspot during what should be the declining phase of solar cycle 25 is not unprecedented, but it is notable. It suggests that the sun has not yet finished with the current period of elevated activity. Whatever the smoothed monthly statistics might indicate, the solar surface remains capable of producing events that could significantly impact Earth. The 11-year cycle itself is actually only half of a longer pattern. Each cycle, the sun's magnetic polarity reverses. During cycle 24, the sun's north magnetic pole was positive, and its south pole was negative. During cycle 25, these polarities have flipped. It takes 2 complete 11-year cycles for the sun's magnetic field to return to its original configuration, making the true period of the solar magnetic cycle approximately 22 years. This 22-year pattern, called the Hale cycle, after the astronomer who discovered it, has been proposed as a factor in extreme space weather events. Some researchers have suggested that the most powerful solar storms tend to cluster at certain phases of the Hale cycle, perhaps when the orientation of the sun's magnetic field relative to Earth is particularly favourable for energy coupling. The evidence for this hypothesis is mixed, but it represents one of many attempts to find predictable patterns in what often seems like chaotic solar behaviour. What we can say with confidence is that solar maximum represents a period of elevated risk. The number of active regions on the solar disk increases, the probability of M-class and X-class flares rises, the chance of Earth-directed coronal mass ejections goes up. During solar maximum, space weather forecasters issue more watches and warnings, satellite operators monitor their systems more closely, and power grid managers remain alert for signs of geomagnetic disturbance. The current situation exemplifies both the risks and the uncertainties of solar maximum. We have a massive sunspot complex facing Earth, one of the largest in a decade. We have already experienced multiple significant flares from this region and its neighbours. A coronal mass ejection is currently in transit, expected to produce G3, or possibly higher geomagnetic storming. All of this is occurring at a time when the sun should be calming down according to statistical predictions. But here is the uncomfortable truth that solar physicists grapple with every day. We cannot predict when or whether a specific sunspot will erupt. We can assess probabilities. We can monitor magnetic complexity. We can track the evolution of active regions across the solar disk. What we cannot do is say with certainty that a particular region will or will not produce a major flare in the next hour, the next day, or the next week. The physics of magnetic reconnection involves instabilities that develop on timescales too fast, and at spatial scales too small for our instruments to track in real time. A sunspot can sit quietly for days, building magnetic stress, and then explode without warning. Conversely, a region that appears primed for eruption can rotate harmlessly off the solar limb without ever producing the expected event. The sun keeps its own counsel, and our predictive capabilities, while vastly improved from even a decade ago, remain fundamentally limited. This is why the watch and warning system exists. NOAA's Space Weather Prediction Center monitors the sun continuously, analyzing imagery from multiple spacecraft, tracking the evolution of active regions and issuing forecasts that attempt to quantify the probability of various space weather events. When they say there is a 15% chance of X-class flares, they are acknowledging both the potential for extreme events and the uncertainty inherent in predicting solar behavior. The cycle we cannot escape is not just the 11-year oscillation of sunspot numbers. It is the perpetual cycle of risk and uncertainty, of watching and waiting, of knowing that at any moment the sun could produce an event that would test the limits of our technological resilience. We are currently in a period of elevated risk. The sunspot numbers may be declining from their August peak, but the massive active region on the Earth-facing disk demonstrates that the danger has not passed. Solar Cycle 25 has exceeded expectations. It has produced more flares, more sunspots, and more intense activity than the expert panel predicted in 2019. Whether we have truly passed solar maximum, or whether there are more surprises in store, only time will tell. What we know for certain is that until this cycle reaches its minimum, likely sometime around 2030, we remain in a period when the sun is capable of producing events that would challenge everything we have built. The cycle continues, the sun breathes, and we watch and wait and hope that when the next great storm comes we will be ready. What Mars saw before we did. In the vast loneliness of the Martian surface, a robot named Perseverance continues its patient exploration of Jezero crater. The rover, which landed in February of 2021, is primarily tasked with searching for signs of ancient microbial life and collecting rock samples for eventual return to Earth. But like all NASA Mars missions, Perseverance carries instruments that monitor the space environment around it, tracking radiation levels and solar activity from a vantage point tens of millions of miles from Earth. Approximately 1 week before the sunspot, complex AR4294 rotated into view from Earth. Perseverance detected it from Mars. This detail, which might seem like a minor technical footnote, actually illuminates something profound about our ability to monitor solar threats. The sun rotates on its axis once approximately every 27 days as seen from Earth. A sunspot that emerges on the far side of the sun, invisible from our planet, will eventually rotate into view over the eastern limb. During the days or weeks when that active region is pointed away from Earth, we are essentially blind to its development. We cannot see it forming. We cannot track its magnetic evolution. We have no warning that a potentially dangerous structure is building on the solar surface until it swings around to face us. But Mars, depending on its orbital position, can sometimes see parts of the sun that are hidden from Earth. When the geometry is favourable, spacecraft on or around Mars can provide advance warning of active regions before they rotate into our line of sight. This is exactly what happened with AR4294. The Perseverance rover, looking at the sun from its position on Mars, detected the emerging sunspot complex days before Earth-based observers had any indication it was there. The implications are significant. If we had spacecraft stationed at multiple points around the sun, observing it from different angles, we could maintain continuous surveillance of the entire solar surface. Active regions that currently take us by surprise after rotating onto the Earth-facing disk could be tracked from their earliest emergence. We could monitor their magnetic evolution, assess their flare potential, and issue warnings days or even weeks before the dangerous face of the sun swings in our direction. This concept, sometimes called solar sentinels or a solar ring fence, has been proposed multiple times by space agencies and researchers. The idea is elegant in principle, but challenging in practice. Maintaining spacecraft at positions that provide useful viewing angles requires either heliocentric orbits interior to Earth, placing observers closer to the Sun than our planet, or gravitationally stable Lagrange points that allow continuous observation from fixed positions relative to the Sun. Both options involve significant mission costs and engineering challenges. Currently, our primary eyes on the Sun include the Solar Dynamics Observatory in geosynchronous orbit around Earth, the SOHO spacecraft at the L1 Lagrange point between Earth and Sun, and various instruments aboard NOAA's GOES satellites. These platforms provide excellent coverage of the Earth-facing solar disk, but limited visibility of regions that have not yet rotated into view. The fact that a rover on Mars, designed primarily for geology and astrobiology, was able to detect the current sunspot complex before Earth-based observers speaks to both the accidental benefits of our interplanetary presence and the gaps in our dedicated solar monitoring infrastructure. We have spacecraft scattered across the solar system for various scientific purposes. When their positions happen to provide useful solar observations, we benefit. But we have not systematically designed a network to ensure continuous all-angle coverage of the Sun. This matters because the worst-case scenario for space weather involves an event from an active region that we did not know existed until it was already pointed at us. Imagine a Carrington-class sunspot complex magnetically loaded and ready to erupt, rotating onto the Earth-facing disk with no prior warning. We would have at most a few days to assess the threat before the region reached optimal geo-effective position. If it erupted immediately upon coming into view, we might have less than a day of warning before the flare and CME were on their way. The Perseverance observation of AR4294 gave us a preview of what systematic early warning could look like. Solar physicists knew the region was coming. They had time to prepare observations, to alert space weather forecasters, to begin monitoring for signs of activity even as the structure was still rotating into view. This advance notice did not change the fundamental physics of the sunspot, but it improved our situational awareness and allowed for more careful tracking of the region's evolution. Amateur astronomer Patricio Leon, who has been following the current sunspot complex since its emergence, noted that it required more than 2 full days to rotate entirely past the eastern limb of the Sun. The sheer size of the structure meant that it was visible from Earth for an extended period during the rotation process. But even so, the earlier stages of its development, the initial emergence of magnetic flux from below the solar surface, occurred while the region was still hidden from our view. The Mars detection also highlights the growing capability of instruments designed for purposes other than solar monitoring to contribute valuable space weather data. Perseverance carries a radiation assessment detector that measures the energetic particle environment on the Martian surface, primarily to inform future human mission planning. But the same instrument that measures particles from distant cosmic ray sources can also detect the enhanced radiation that accompanies solar flares and CMEs. When the Sun erupts, Mars missions see the effects and can report them back to Earth. This distributed sensing capability has become increasingly important as our presence throughout the solar system has expanded. Spacecraft at Venus, Mercury, Mars, Jupiter, and beyond all carry instruments that can detect solar events. When a major eruption occurs, we can track the propagation of the CME through interplanetary space by observing its effects at multiple locations. This provides a kind of 3-dimensional view of solar storms that was impossible when our only sensors were based at Earth. The Parker Solar Probe, which is currently conducting the closest ever observations of the Sun, is scheduled to make its nearest approach in December of 2024, passing within just 6 million kilometers of the solar surface. This mission is providing unprecedented data about the solar corona and solar wind, information that will improve our understanding of how CMEs accelerate and propagate. The European Solar Orbiter mission, launched in 2020, is conducting observations from an orbit that takes it both close to the Sun and high above the ecliptic plane, providing views of the solar poles that have never before been possible. These missions are revolutionizing our understanding of solar physics, but they are scientific rather than operational assets. They were not designed to provide continuous real-time monitoring for space weather forecasting. The data they collect is invaluable for research, but often takes time to process and analyze. What we need for operational forecasting is something different, a network of spacecraft dedicated specifically to space weather surveillance, positioned strategically to provide continuous coverage of the entire solar surface and equipped with instruments optimized for real-time event detection and warning. The investment required would be substantial but not unprecedented. We already operate weather satellite constellations that provide continuous monitoring of Earth's atmosphere from multiple orbital positions. The same principle could be applied to solar monitoring, with spacecraft at the L1, L4 and L5 Lagrange points, plus additional assets in heliocentric orbits, providing all-angle coverage of the Sun at all times. Until such a network exists, we will continue to rely on fortuitous observations like the Perseverance detection of AR4294. We will continue to be surprised by active regions that emerge on the far side and rotate into view fully developed and potentially dangerous. We will continue to operate with less warning than we could have if we invested in the infrastructure that modern space weather forecasting requires. The sunspot that Mars saw before we did may or may not produce a catastrophic event, but the next one might, and the one after that. Somewhere out there on the far side of the Sun, the next great solar storm may already be building. We just cannot see it yet. The storm that almost was. On July 23, 2012, the Sun unleashed a monster. A coronal mass ejection of extraordinary power blasted away from the solar surface, accelerating to speeds exceeding 3,000 kilometers per second, carrying enough energy to rival the Carrington event itself. It was the kind of solar storm that space weather scientists had warned about for decades, the kind that could devastate power grids, disable satellites, and send modern civilization reeling. It missed Earth by approximately 9 days. 9 days in celestial terms is the difference between the rotation of the Sun carrying the eruption site away from the Earth direction and carrying it toward us. If the active region that produced this CME had erupted roughly 1 week earlier, when it was pointed at our planet rather than away from it, the consequences would have been severe. We would not be speculating about what might happen in a Carrington-level event. We would be recovering from one. The July 2012 event has become a touchstone in discussions of space weather risk. It demonstrates that the Sun remains capable of producing superstorms comparable to historical extremes. It shows that such events are not confined to the distant past, but can occur in the modern era, when our vulnerability to them has increased by orders of magnitude. And it serves as a sobering reminder that our safety from extreme space weather depends, to a significant degree, on luck. The CME originated from active region 11520, a magnetically complex sunspot group that had been producing flares for several days. The eruption that launched the massive cloud of plasma was associated with an X-class flare, though because the region was on the far side of the Sun relative to Earth at the time, our instruments could not directly measure its intensity. Analysis of the CME itself, using data from the stereo spacecraft that observed it from a favourable angle, suggested it was among the most powerful solar eruptions recorded in the space age. The transit time from Sun to Earth, had the CME been directed at us, would have been remarkably short. The initial speed measurements indicated the leading edge was travelling at approximately 2,500 kilometers per second. At that velocity, the plasma cloud would have reached Earth in roughly 17 to 18 hours, comparable to the transit time of the Carrington event CME. This rapid propagation was likely enabled by a previous CME that had occurred hours earlier, clearing the ambient solar wind out of the path, exactly the mechanism that scientists believe enhanced the speed of the 1859 event. Daniel Baker, director of the Laboratory for Atmospheric and Space Physics at the University of Colorado, published an analysis of the 2012 event that reached stark conclusions. He estimated the storm would have caused extensive damage to satellites, potentially disabling a large fraction of the GPS, communication, and weather monitoring constellations. The geomagnetically induced currents would have stressed power grids across multiple continents, likely causing transformer failures and widespread blackouts. The economic impact could have reached or exceeded $2 trillion. Recovery would have taken years. We dodged this bullet purely by chance. The Sun does not aim. It does not care whether Earth is in the path of its eruptions. Active regions rotate across the solar disk, erupting when internal magnetic stresses reach critical thresholds, and the direction of those eruptions depends entirely on where the region happens to be pointed at the moment of the event. A region on the far side of the Sun produces a CME that races harmlessly into interplanetary space, posing no threat to Earth. The same region, a week earlier or later in its rotation, produces a CME that strikes our planet head-on. The July 2012 near-miss was not unique. Throughout the history of solar observation, there have been numerous powerful eruptions that occurred when the Sun was pointed away from Earth. We know about them because our monitoring spacecraft can detect events regardless of their direction, and because some of those events were observed by spacecraft at other locations in the solar system. What we do not know is how many potential catastrophes we have narrowly avoided without ever realizing it. The statistics are sobering. Various estimates place the probability of a Carrington-class event within any given decade at somewhere between 1 and 12%. That range reflects genuine uncertainty about how often such extreme events occur and how we should define the threshold for Carrington-class magnitude. But even the lower estimates imply that over a multi-decade period, a severe event becomes quite likely. If the probability is 5% per decade, then over a 50-year span, the cumulative probability exceeds 20%. Over a century, it approaches 40%. These are not small numbers. We insure against risks with far lower probabilities. We build earthquake-resistant structures in seismic zones despite the uncertainty about when the next major quake will strike. We maintain fire departments even though any particular building is unlikely to catch fire on any particular day. The actuarial logic that governs prudent risk management suggests we should be investing heavily in space weather resilience. The fact that we are not suggests a collective failure to take the threat seriously. The 2012 event also highlighted the importance of the Stereo mission, a pair of spacecraft that orbit the Sun at roughly Earth's distance, but at positions ahead of and behind our planet in its orbit. These spacecraft can observe portions of the Sun that are hidden from Earth, exactly as Perseverance on Mars observed AR4294 before it rotated into our view. When the July 2012 CME erupted, Stereo A was positioned to observe it in profile, capturing the expansion and propagation of the plasma cloud as it raced outward through the solar system. Without stereo, we might not have known the full magnitude of what we dodged. The event would have been recorded as a far-side eruption of some undetermined size, one among many such events that occur during solar maximum. Instead, we have detailed measurements of its speed, its mass, its magnetic configuration, all the parameters needed to assess what it would have done had it been aimed at Earth. The data paint a picture of a storm that would have rivaled or exceeded the Carrington event in intensity. The speed was comparable. The magnetic structure was complex and energetic. The quantity of material ejected was enormous. All the ingredients for catastrophe were present. Only the geometry was wrong. Wrong from the Sun's perspective in terms of hitting its target, but fortunate from our perspective in terms of avoiding disaster. Since 2012, the space weather community has worked to ensure that this near miss is not forgotten. The event is cited in reports, referenced in policy discussions, and used as a case study in training exercises. When agencies conduct tabletop simulations of severe space weather events, the 2012 eruption provides a realistic template for what a modern Carrington-class storm would look like. But memories fade. Institutional attention shifts to more immediate concerns. The officials who were alarmed by the 2012 analysis have retired or moved on. New decision-makers, unaware of how close we came, allocate budgets based on threats that feel more tangible and immediate. The blind spot that allows us to ignore space weather risk regenerates itself with each passing year of quiet sun. The current sunspot complex facing Earth is a reminder that the threat has not gone away. The CME currently in transit is a smaller-scale demonstration of the processes that could, under different circumstances, produce a civilization-altering event. We are playing a game of celestial roulette, spinning the cylinder each time an active region faces Earth, hoping that the chamber is empty. In July 2012, we got lucky. The chamber was empty. The bullet passed harmlessly by. But the gun is still loaded, and the Sun keeps pulling the trigger. Sooner or later, our luck will run out. The question is not whether we will face another Carrington-class event. The question is whether we will be prepared when it comes. watching the sleeping giant. As this documentary reaches you, the sunspot complex that has commanded our attention for the past week continues its slow rotation across the Earth-facing disk of the Sun. AR4294, along with its magnetically intertwined companions, AR4296 and AR4298, remains one of the most impressive solar features observed in the past decade. Its dark cores, each one capable of swallowing Earth, continue to churn with magnetic energy. Its beta-gamma-delta classification has not changed. The potential for a major eruption has not diminished, and yet, for the past several days, the region has been remarkably quiet. This is the paradox that haunts space weather forecasters. The largest, most magnetically complex sunspots do not always produce the largest flares. Sometimes they sit peacefully for days, building stress without release, before rotating off the western limb and disappearing from view. Other times, they explode repeatedly, hurling energy and plasma into space with each successive eruption. There is no reliable way to predict which behavior a given region will exhibit. The current forecast from NOAA's Space Weather Prediction Center reflects this uncertainty. M-class flares are considered likely, X-class flares are possible. Beyond these probabilistic statements, we cannot say much with confidence. The Sun keeps its own schedule. What we can say is that the threat we have discussed throughout this documentary is not hypothetical. The Carrington event happened. The Quebec blackout happened. The 2012 near miss happened. Miyake events have left their signatures in trees around the world, evidence of storms far exceeding anything in recorded human history. The Sun is capable of producing events that would fundamentally alter the functioning of modern civilization, and we have done remarkably little to prepare for that possibility. The CME launched by the M8.1 flare on December 6th is expected to arrive at Earth within hours of this recording. NOAA has issued a G3-strong geomagnetic storm watch, indicating that significant auroral activity is likely and some infrastructure impacts are possible. This event will almost certainly not be catastrophic. It will produce beautiful displays in the northern sky for observers at high latitudes. It will cause minor fluctuations in power grids and brief disruptions to high-frequency radio communications. Satellite operators will monitor their systems closely and implement protective measures as needed. Life will go on. But each such event is a reminder that we orbit a star capable of great violence, a reminder that the infrastructure we depend on was built without serious consideration of space weather hazards, a reminder that our continued safety depends on a combination of physics we cannot control and preparations we have largely failed to make. The sunspot complex will continue rotating toward the western limb over the coming days. It may erupt before it disappears from view, or it may slip quietly around to the far side of the Sun, building energy for a future display. If it erupts while still facing Earth, we will have minutes of warning for the radiation effects and hours to days of warning for any associated CME. That timeline is sufficient for operational responses, shutting down satellites, reducing power flows, alerting authorities, but insufficient for the kind of fundamental preparations that would make a real difference. The broader lesson of this moment is that we live in a narrow window of technological vulnerability. 200 years ago, a Carrington-class event would have been a spectacular light show and nothing more. The auroras would have dazzled observers, telegraph wires would have sparked and smoked, but the basic functioning of society would have continued uninterrupted because society did not yet depend on electrical technology. 200 years from now, if we are thoughtful about how we develop, we might have power grids hardened against geomagnetic storms, satellite constellations designed with redundancy and rapid replacement capability, and early warning systems that provide days or weeks of notice before a major event arrives. The vulnerability we currently face is a consequence of our particular moment in technological history, advanced enough to depend on fragile systems, but not yet advanced enough to protect them. The question is whether we will use the time we have to close that gap. Every year without a major event is an opportunity to invest in resilience, to harden critical infrastructure, to develop the monitoring capabilities that would give us maximum warning of incoming threats. Every year without a major event is also an invitation to complacency, to assume that because nothing bad happened yesterday, nothing bad will happen tomorrow. We know the Sun is capable of producing extreme events. We know our infrastructure is vulnerable. We know the economic and human costs of a Carrington-level storm would be staggering. What we do not know is when the next such storm will occur. It could be decades away. It could be next week. The only honest answer is that we cannot predict it with any precision. What we can do is prepare. We can invest in transformer protection. We can develop strategic reserves of critical components. We can expand our solar monitoring network to provide early warning of threats developing on the far side of the sun. We can conduct the research needed to better understand and predict extreme space weather events. We can take the threat seriously rather than relegating it to the category of exotic risks that we prefer to ignore. The sleeping giant on the face of the sun may wake at any moment, or it may slumber peacefully until it rotates out of view. Either way, it will return. The sun rotates once every 27 days, bringing active regions back into Earth's line of sight on a regular schedule. And even if AR4294 fades into obscurity, other active regions will emerge. Solar cycle 25 is not yet over. Solar cycle 26 will follow. The sun will continue its 11-year rhythm of activity and quiet for as long as the hydrogen fuel in its core holds out, which is to say for the next 5 billion years. We are visitors in this solar system, brief flickerings of consciousness on a small planet orbiting an average star. Our civilization, for all its complexity and sophistication, has existed for only the blink of a cosmic eye. The sun was here long before us and will remain long after we are gone. Its processes operate on timescales that dwarf human history. Its eruptions release energies that dwarf anything our technology can produce. And yet, here we are, watching, measuring, trying to understand, trying to predict, trying to protect ourselves from forces that do not know we exist and would not care if they did. The monitors will continue tracking AR4294 until it disappears over the western limb. The forecasters will continue issuing their probabilistic assessments. The satellite operators and grid managers will continue their vigilant watch. And somewhere out there, below the visible surface of the sun, magnetic flux tubes are rising through the convection zone, building the active regions of tomorrow. Some of those future regions will be small and inconsequential. Others will be giants, comparable to or exceeding the monster currently facing Earth. Eventually, inevitably, one of them will erupt at the precise moment when it is pointed directly at our planet. When that happens, we will learn how well we have prepared. We will learn whether our infrastructure can withstand the assault. We will learn whether our civilization is resilient or fragile. Until then, we watch, we wait. We hope that when the sleeping giant finally wakes, we will be ready. Thank you for joining me on this journey through the science and mystery of solar storms. I hope you found it illuminating, perhaps a little unsettling, and ultimately thought-provoking. If you enjoyed this exploration, please remember to like and subscribe so you never miss our future documentaries. Share your thoughts in the comments below. Tell me what aspects of space weather you would like to explore further. Tell me about the auroras you have seen or hope to see. Tell me how you think we should prepare for the inevitable day when the sun reminds us who is really in charge. Please remember that this documentary represents a synthesis of current scientific understanding combined with informed speculation about future possibilities. It is intended to educate and engage rather than to frighten. The probability of a catastrophic solar event on any given day is low. The probability of such an event within our lifetimes is higher but still uncertain. What is certain is that preparation is wiser than denial, and that understanding is the foundation of resilience. The sun will rise tomorrow, as it always does. Its light will warm our faces. Its energy will power our world. And somewhere beneath its seemingly placid surface, the forces that could reshape our civilization will continue their slow, patient accumulation. Sleep well tonight, dream of auroras dancing across northern skies, and know that out there, 93 million miles away, the sleeping giant breathes. Good night.